Hi everyone, my name is Nazar and you are watching the first video of my course, Software Development from Scratch, on my channel, Hardware Developer. In this course we will start with the basics. We will talk about what information is, how number system works, what logic is, and how simple electrical circuits can store and process data. Then we will build a very simple computer model. After that, we will create our own small programming language, based on a few basic machine commands. This course is for people who have never written code before. It is also for developers who started with high-level languages like Java, Python, C# or JavaScript, but never learned what happens inside a computer. Maybe you already know that computers work with zeros and ones. But in this course we will answer a more important question: why does it work this way and how does it actually happen? If you studied computer science at university, some parts of this course may be familiar to you. A lot of great books have been written about how hardware works. I'll add links to them in the description below. This course is made first and foremost for you to learn. And if it's easy to you to absorb the information by reading, then by reading those books you will know everything this course covers and more. But for those who prefer video, let's continue. To explain this topic I will use a simple made-up story. All the characters in this story are not real, and the events in this story never really happened. Your job is not to remember the story itself. Your job is to understand the main idea behind it. I also want to be honest with you. Some good examples and explanation in this course are based on books that help me understand these topics better. I changed them a little and adapt them for this course. So let's begin. Let's imagine a stock exchange in London at the end of the 19th century. Information back then was extremely valuable, because the first person who learned something useful could close a very profitable deal. Two gentlemen work at this exchange. Let's call them Tom and Harry. Tom and Harry used letters to pass information between each other, but at heart they were great engineers. And even though life had made them exchange traders, they were always trying to build something new. Tom would write a letter to Harry and send it with a trusted messenger or butler. Harry would read it and do the same in return. But while the messenger or butler was delivering the letter, he might learn something he wasn't supposed to know. Let's not worry for now about how to secure the letters for being reading by outsiders. The guys decided to come up with something grand, a sound-based communication device. A sound-based communication device. And how do you transmit anything useful with it? Thomas actually can put a handle here and a bell rings on Harry's end. Yeah, here. For now, let's not worry about distance or the trouble of stringing the chords. We need to focus on how to actually transmit something useful with sound, some kind of information. So they went and came up with a simple method. Let's just give each letter a sequential number. However many letters we have, those are the numbers. Letter A is 1, letter B is 2, letter C is 3, letter D is 4, E is 5, etc. Then you can write a message on paper, like say hello, then swap each letter for its number and ring the bells that many times for each letter. For example, the letter H is number 8, so you ring 8 times. E is 5. You get the idea, yeah? We also need to agree on the pauses between the letters and between the words. This method is way too expensive. To say hello, you would have to ring the bell 52 times. Your head would already ache just for the greeting. Was the device useful at all? In one way, yes. Only the people in the conversation understood the information, because they know how it encoded and decoded. To everyone else, it was just a meaningless jillion of bell. Very roughly, this is the basic method of transmitting information that's still used today. It's like a creation, encoding, transmission, receiving, decoding, and presentation or read. Yeah? This method was pretty bad, so alternatives were needed. Electricity was at the peak of the hype, and engineers just could not resist using it in their inventions. Let's first recall some school physics and look at how electrical circuits work. I won't explain things at the level of atoms. You can read about that in books I mentioned at the start. If the circuit is open, the lights doesn't turn on. If it's closed, it lights up. Now we can run wires between the two people in the conversation, give one a switch and the other a lamp. With this new device we can use the same encoding and decoding system as before, each letter corresponding to its sequential number, but the transmission speed changed for the better. And on top of that, it's now much quieter. By the way, as long as only one person has a button and the other has a lamp, the type of connection is called simplex, meaning one person can only send at a time and the other can only receive. Now we can run a device to the other person as well, and we get a half-duplex connection. In other words, if Tom is sending a message, Harry listens and can't send at the same time. And the same is true the other way around. Only one person sends at a time, like a walkie-talkie. The transmission method changed from sound to light, but the excessiveness stayed. The problem needs solving too, so the guys went to ChatGPT and found Morse code. In Morse code, each letter corresponds to signals in different lengths. For example, A is a short-long, K is a long-short-long. Now, the longest letter could be transmitted in at most 5 flashes of the lamp, which is already better. Of course, again, we need to agree on the pauses between words and letters to make it clearer. The principle stayed the same. Both gentlemen need a dictionary to encode and decode a message. Everything have been fine, but over time the distance between them grew. Maybe one of them moved farther away or something, and engineers get another problem. The signal was very weak and got lost over distance, and this problem needed solving. A device called relay will help solve it. This device uses an electromagnet. It also has its own power source. When current flows through the electromagnet, the device closes the circuit. The current can continue to flow, but now it comes from a different power source. Let's see how it looks on a diagram. We have a signal from Tom's house. It arrives at the relay switch. This electromagnet started working and closed this switch, and we have this circuit closed. It's like a repeater, yeah? On the telegraph it's like a repeater of the signal. So the relay effectively repeats every on and off signals of the lamp. And so our engineers now had a communication device in their hands, one that can be scaled up. Meanwhile, the encoding, sending, receiving and decoding were all done by hand. Everything could have been fine, but the guys wanted to send message better. Because Morse code was going out of fashion, and they always wanted to make something new. And to optimize transmission, they had to figure out something more complex: number systems. The main job of traders at the exchange was counting dollars. And to figure out how to count dollars properly, we will look at many options, namely, the first system for counting dollars looks roughly like this. Drawing tally marks on wood or tying knots in cords was quite enough. Let's take a closer look at the tally marks. For ancient people, the easiest way to count dollars was with simple strokes, and for easy reading, you could cross them out, like this. The Romans thought dollars were better counted using their own system. So $15 we can depict in the counting system of the ancients and also in the Roman one. Next, let's look at the number system we are used to. According to historical records, it was invented by Sumerians or the Babylonians. It is based on digits and their positions. In other words, this kind of number system is called positional. In principle, you could use anything instead of digit. But since we are more used to Arabic numerals, this system feels more familiar. It is based on 10 digit. And notice, there is no single digit 10 in it. We count like this, from 0 to 9, yeah? And then we run out of digits. So we increase the place value. That is the number of tens. Alright, things are about to get tricky. The whole beauty of a positional number system is that you can build it in any base. It doesn't have to be based on 10 digits. There can be as many as you like, 3, 7, 9. If the base is 10 digit, or cats, or symbols, then each next place will be a power of the base. In the decimal system, each place carries the weight of tens, hundreds, thousands, and so on. So everything depends on the digit position. The digit 1 can mean 1, or number of tens, or number of hundreds, yeah? The digit 4 can mean just 4, or a number of tens or number of thousands. It depends on the position. In other words, it all depends on where you add another digit, in which position of the number. The number 2020, that is a quantity. We can express with 4 digits. This system is convenient for us because we have 10 fingers. But is that really the reason? Who remember how long they spent learning to count? Or rather, how many years? In kindergarten and the early school grades, if we had fewer fingers, we would count differently. Let's look at another number system, based on 8 digits. Same catch again, there is no single digit 8 in it. Also this number system called octal. We count the same way, 0, 1, 2, 3, 4, 5, 6, 7, and we have run out of digits. What do? We already know. We use this in the decimal system. We increase the place value. Only now our place, it's not tens, but eighths. So the digit 1, the one of the left in the second place, now points to the number of eighths. Because, as I said, if the base of the system is 8, then each place is a power of the base. Let's compare these two systems. They are similar, and probably if our parents hadn't taught us to count on our fingers from birth, we would count just as easy in a base 8. Look at the number 8 in decimal system. In octal these digits are 1 and 0, but this isn't 10, as it might seem. It is a completely different number. The digit 0 is the number of ones, and the digit 1 is the number of eighths. Here is an example of the position of number in octal. The first place is ones, then the number of eighths, then the number of 64s, then the number of 512s. We can convert into a convention system just by multiplying and summing. 3 times 512s, 7 times 64s, 4 times 8, and 1 times 4. That's how we get the number in our convention decimal system. Let's mark the base of the system slightly below the number itself. That means the value of this number is the same. It's just a different representation. We get the number 2020 in decimal and the number 3744 in octal. And the number itself stayed the same. The value is the same. It's just written in a way that's unfamiliar to us. So our $15 can now be written as 15 in decimal and 17 in octal. Now let's look at the most important number system for us. Don't worry, in real life you won't have to work with it. But it's probably worth seeing how it's built. The binary system is based on two numbers, 0 and 1. Surprise, surprise. When we run out of numbers, we increase the place value, just like in decimal and octal. Here too, everything depends on the digit position in the number. Also, each next place will be a power of 2, the number of ones, the number of twos, the number of fours, and the number of 8. The nicest part is that you don't have to multiply anything, because the quantity is always either 0 or 1. So, if there is 1 in a place, that 1 is a quantity itself. Let's add this system to our counts. Now, the same amount of dollars is shown in the binary system. Here is an example of the place in the binary system. Let's look at how to convert from it into our convenient decimal. Each place has its own base. And since we only have the digit 1 or 0, the number itself is a quantity of 2, of 4, of 16. So we add up the value of every place that has a 1, going right to left. 1 plus 2 plus 4 plus nothing plus 16 plus 32 plus 128. And we will have the number in our convenient decimal system. If we set all the ones in this example, we get 255 in decimal. One place of this number in computer terminology is called a bit. 8 bits make up a byte. 1 byte can hold a number up to 225 in decimal. Let's take a closer look at the places themselves and remember why we need all this in the first place. The binary system maps very nicely onto electrical device, because they have only two states, on and off. And Tom and Harry were just planning to improve their transmission device. They could send more information faster if they used 8 lamps at once instead of 1. Later, this number system will help them build a device far more complex than what they have now. One that automates their work. But that is for the future. The guys put together 8 lamps and 8 switches. Very roughly, the switches might look like this. And the device itself something like this. Now all over again. We run wires between the two people. There will be 8 of them. How strange, since the twisted pair in your apartment also has 8 wires. There is probably something to that. We get rid of the night cable using the ground. We get a device capable of transmission information from house to house. We run the wires as far as we need. If the signal isn't strong enough, we can use the repeater we already know about. Now we can look at the new way of encoding information, since we have as many as 8 lamps. The guys searched and came up with something at random. Let's do it like this. And they made a table like this. The letter A is encoded at 01000001, and which matched the number 65 in decimal. You could also transmit space and the line break, like here, or like some special characters, which made it possible to send not just text, but also how it should be formatted, with spaces and line breaks, yeah? When the lamps light up for the person receiving the message, they manually write down which ones lit up, and their notes look roughly like this. Imagine that copying one letter into a notebook, a letter made of 8 lamps, that is 8 bits, takes 5 seconds. Then, in a minute, you can receive 12 letters. Since each letter has 8 bits, we have got a communication device capable to transmitting information at a speed of 96 bits per minute, or roughly 1.5 bits per second. With this binary code in hand and a table with the dictionary, you can decode a message whenever it's convenient, not always right away. Later, Tom and Harry managed to convince everyone that this was the one true correct encoding system, and this table was adopted as the ASCII encoding standard. So if you see a letter A on a screen somewhere, in decimal that's 65, and you already know how to convert 65 to binary. Which means that with 8 lamps or 1 byte you can transmit that information. What did we learn today? What information can look like? How manual encoding and decoding the information works? What alternative number system exists? How a relay works? Next, we will keep improving and automating the device built by the engineer geniuses, Tom and Harry.